When dealing with multiple service panels fed from a single meter, it's crucial to understand the proper way to size the conductors. In the case of a 320/400 amp meter feeding two 200 amp main breaker service panels in a commercial building with a 240 volt single phase system and a calculated building load of 308 amps, we need to verify if 4/0 aluminum U/RHW conductors are adequate for each panel, keeping in mind 75-degree terminations and referencing 240.4b. The National Electrical Code, or NEC, provides the guidelines for safe and compliant electrical installations. Conductor ampacity is a fundamental concept. Ampacity refers to the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC provides ampacity tables such as this found in 310.15b16, which lists the allowable ampacities for various conductor types and sizes based on their insulation type and temperature rating. For 4/0 aluminum U/RHW conductors with 75-degree terminations, the ampacity is 240 amps. This means that each 4/0 aluminum conductor can safely carry up to 240 amps in the specified conditions. The calculated load of the building is 308 amps. This figure represents the total anticipated current draw of all the electrical equipment and devices connected to the electrical system. It's essential to accurately calculate the load to ensure that the conductors and overcurrent protection devices are adequately sized. Overcurrent protection is a vital safety measure in electrical systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage and potential hazards. The NEC mandates that overcurrent devices be sized appropriately to protect the conductors they serve. A key rule to remember is that the overcurrent device should not be sized larger than the ampacity of the conductor it protects, unless specific exceptions apply. NEC section 310.15b16 addresses the adjustment and correction factors for conductor ampacity. It states that the overcurrent device must be sized for no more than 80% of the conductor ampacity under certain circumstances. This rule is particularly relevant when dealing with continuous loads. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. If the load is considered continuous, the overcurrent device must be derated to 80% of the conductor ampacity to prevent nuisance tripping and ensure conductor longevity. In this scenario, even though the load on each individual panel is less than 180 amps, the calculated building load of 308 amps exceeds the combined ampacity of the 4/0 aluminum conductors if we apply the 80% rule. Firstly, we determine the allowable ampacity of the 4/0 aluminum U/RHW conductors at 75 degrees, which is 240 amps. Secondly, we apply the 80% derating factor to the conductor ampacity. 80% of 240 amps is 192 amps. This means that each 4/0 aluminum conductor can only be loaded to a maximum of 192 amps when considering the overcurrent protection requirement. Thirdly, we compare the calculated load to the adjusted conductor ampacity. The calculated building load is 308 amps, which is significantly higher than the 192 amps allowable ampacity per conductor after applying the 80% rule. Therefore, the 4/0 aluminum U/RHW conductors are not suitable for this application. The overcurrent device protecting these conductors would need to be sized at 192 amps or less, which is insufficient to carry the 308 amp building load. In order to properly size the conductors for this application, several factors need to be considered. These include the total calculated load, the conductor ampacity, the overcurrent protection requirements, and any applicable adjustment or correction factors. A larger conductor size may be required to accommodate the calculated load and meet the NEC requirements. It is important to consult the NEC and work with a qualified electrician to ensure that the electrical system is safe, compliant, and adequately sized for the intended application. The correct conductor size can be determined by performing calculations in accordance with the NEC. These calculations will take into account the total calculated load, the conductor ampacity, and any applicable adjustment or correction factors. Once the correct conductor size has been determined, the overcurrent protection device can be sized accordingly. When dealing with multiple service panels, it's crucial to consider the total load in the system, not just the individual panel loads. The conductors feeding the panels must be sized to handle the total load. In this case, the total calculated load of the building is 308 amps. This means that the conductors feeding the panels must be capable of carrying at least 308 amps. Since the 4/0 aluminum U/RHW conductors have an ampacity of only 240 amps, they are not suitable for this application. Larger conductors are required to handle the total load. It's important to remember that the NEC is a minimum standard. In some cases, it may be necessary to use larger conductors than required by the NEC to provide additional capacity or to improve voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Therefore, it's important to consider voltage drop when sizing conductors. In addition to conductor sizing, it's also important to consider the type of conductors used. Different types of conductors have different ampacities. For example, copper conductors generally have a higher ampacity than aluminum conductors of the same size. Therefore, it's important to select the appropriate type of conductor for the application. The NEC provides tables that list the ampacities of various types of conductors. These tables can be used to select the appropriate conductor size and type for a particular application. It's also important to consider the ambient temperature when sizing conductors. The ampacity of a conductor decreases as the ambient temperature increases. Therefore, it's important to adjust the conductor ampacity for the ambient temperature. The NEC provides tables that list the ampacity correction factors for various ambient temperatures. These tables can be used to adjust the conductor ampacity for the ambient temperature. In addition to ambient temperature, it's also important to consider the number of conductors in a raceway or cable. The ampacity of a conductor decreases as the number of conductors in a raceway or cable increases. This is because the heat generated by the conductors is more difficult to dissipate when there are more conductors in a raceway or cable. Therefore, it's important to adjust the conductor ampacity for the number of conductors in a raceway or cable. The NEC provides tables that list the ampacity adjustment factors for various numbers of conductors in a raceway or cable. These tables can be used to adjust the conductor ampacity for the number of conductors in a raceway or cable. When sizing conductors, it's important to consider all of the applicable factors, including the total calculated load, the conductor ampacity, the overcurrent protection requirements, the ambient temperature, and the number of conductors in a raceway or cable. By considering all of these factors, it's possible to select the appropriate conductor size and type for a particular application and ensure that the electrical system is safe, compliant, and adequately sized for the intended application. In summary, the 4/0 aluminum U/RHW conductors are not adequate for this application because the calculated building load of 308 amps exceeds the allowable ampacity of the conductors after applying the 80% rule. Larger conductors are required to handle the total load and meet the NEC requirements. Consulting with a qualified electrician is essential to ensure safe and compliant electrical installation. Consider that the location is Washington State and North Carolina. These states adhere to the National Electrical Code, so the standards discussed are applicable in both locations.